Good morning, everyone. I'm Professor Sever, and today we're going to consider a derivative problem in using the absolute value, and really in terms of exploring the product rule and its applicability to this problem. Okay, so let's go ahead and begin. Let's see what we're working on. We're going to try to take the derivative of this function, x times the absolute value of x, and via the product rule, and we're going to discuss whether this function is differentiable at 0. Now, let's see what knowledge we need to do this. Well, we're going to use the fact that we have a derivative rule for the absolute value. We know that the absolute value is not differentiable at 0. The absolute value function is not differentiable at 0. And of course, we know the product rule. That's kind of the point of this demonstration, is to explore the product rule in a problem like this. So really, what does the product rule say? Well, it says basically if both f and g are differentiable at x, then you can compute the derivative thusly: the derivative of the first times the second plus the derivative of the second times the first. That's typically how we say it. But the kicker here is, the key is, well, these two functions are not differentiable everywhere. This one, the absolute value function, as we've stated here, is not differentiable at x. So let's see what happens. Okay, so first, let's just apply the product rule and see what we get. All right, so in doing so, this would be our first function. Absolute value, if we're applying it strictly, would be our second function. Okay, so by the product rule, we would see that h prime of x is equal to the derivative of the first, which is f prime of x, which is just 1, times the second function, which is just simply g of x, which is the absolute value of x, plus, and that plus comes from this plus right here of the product rule, the derivative of the second function. Now that's where we need our knowledge base. So I'm going to use the fact that I know that the derivative of the absolute value function is x over the absolute value of x for an x non-zero, and then again times the first function. Okay, so if we're matching it up, this was f prime, this was the original function g, this piece right here, and I mean this whole piece here, is g prime, and then this piece is just the original function f. Okay, so let's do some algebraic simplification, but first we need to state this is for x non-zero. All right, that's the key here. Well, certainly you can't use 0 in this expression, but furthermore, this statement says we don't know what's happening at 0, and a mistake, a logical mistake, and some people make it, is that they would then say, well, h, which is the product, is not in fact differentiable at 0 because of this. Well, that's actually not true. All we know is the product rule can't tell us anything about the differentiability of h at 0, because one of the functions was not differentiable at 0. Okay, let's simplify using some algebra. This is just the absolute value of x. 1 times anything is itself. And if we want to simplify, we have x times x is x squared. Now x squared is non-negative, so that's the same as the absolute value of x squared over the absolute value of x. And you can see what I'm about to do here. I'm going to cancel. And so we get this, which we'll simplify as 2 absolute x. Again, x is not 0. And you can't just say, well, since the denominator is now gone, the function is differentiable at 0, that may not be the case. Okay, so let's simplify this and see what we have. All right, so we have established by the product rule that the derivative of h is 2 absolute value of x for every x that's not 0. Now we don't know what happens at 0. All right, so now how do we find the derivative at 0? Okay. So let's compute that using the definition. So what would that be? All right. So h prime of 0 would be equal to the limit as delta x goes to 0 of h of delta x plus 0 minus h of 0 over delta x. And this is the limit as delta x goes to 0. Now let's see. Now let's look at our function. What's h of 0 here? Let's just do it up here. We can evaluate 0 times the absolute value of 0 is 0. Okay, so we have that. So now, and 0 plus delta x is just delta x. Okay, and now what's h of delta x? Well, remember our function h is x times the absolute x, so this should be delta x times the absolute value of delta x, minus 0, of course, which is 0, over delta x, cancel. Now let's just rewrite. You can see it right now, but let's just let's just recopy it one more step. All right, and now what is the limit as delta x goes to 0 of the absolute value of delta x? That's just the absolute value of 0, which is 0. So f is differentiable at 0, and the result is 0. So h prime of 0 is 0. And finally, if we wanted, we can rewrite. Now you can say h prime of x is equal to 2 times the absolute value of x for all x. For all real numbers x. Now why? Because this formula holds, we get the same result if x is 0. You get h prime of 0 is 2 times the absolute value is 2 times the absolute value of 0, which is 0. So this formula in fact holds for all numbers, including 0, once we've established that. But see, the key to this problem in this exercise is two things. One, the product rule can't tell you that because this right-hand factor is not differentiable at 0. So the result that you get will say nothing about differentiability at 0. Point two, it would be incorrect to claim naively that since this function is not differentiable at 0, the product isn't. It may or may not be, and in this case, it in fact was. Okay, so this kind of shows you that, once again, the product rule is a sufficiency condition. If f and g, here it says differentiable everywhere, that's overkill, because I just used it in a case where that was not true, namely this function is not differentiable at 0. But if f is differentiable at x and g is differentiable at x, certainly the product is differentiable at x, and it can be computed. The derivative of the product can be computed using such a formula, and it doesn't say, it being the product rule, doesn't say anything about what happens if either function is not differentiable at x. And of course, in that case, you'd have to use something else, and that's what we did. I used the definition of the derivative being used here. All right, thank you very much. I'm Professor Sever. I hope you enjoyed this video, and we'll see you next time.